Welcome to this session. In this session, we are going to discuss about how to solve systems of linear differential equations using the concept of eigenvalues and eigenvectors. So in this first introductory chapter, we're just going to define what eigenvalues and eigenvectors are, and then state a few theorems related to how to solve systems of differential equations with eigenvalue, eigenvector method. Then the next session will do specific examples. So let's start by defining what we mean by eigenvalue and eigenvector. So you say, if a vector u which is non-zero and a real number lambda exists such that a times u equals to lambda times this same vector u, i.e. a minus lambda I times this vector u equals to 0 vector, where I is an identity matrix then lambda is called the eigenvalue the matrix A, and then this non-zero vector is called the associated or corresponding eigenvector to this eigenvalue lambda. So this is the main thing, that if there exists a non-zero vector u such that there's a number lambda, that if you have any square matrix A, you multiply by this vector u, then the value is the same as this scalar lambda, and then multiplying by the same vector u. Then if we have that scalar lambda and that vector which satisfy this equation, then we call lambda the eigenvalue. So this is eigenvalue, while this one is the eigenvector. So this equation is sometimes called eigenvalue, eigenvector, equation or relation. So that's the definition of eigenvalue and eigenvectors. Now, so since eigenvalue, eigenvector relation is that if you have a matrix A, you multiply by the eigenvector, you get lambda to the eigenvalue times the same eigenvector u. Now, so for us to and then remember, u is a non-zero vector. That's by definition. Now, taking this to the left-hand side, so we'll have a u minus, now because this lambda, then for us to carry this operation, this a matrix, then we need to multiply lambda to the identity matrix of the same order as A for us to carry out that operation. Now, this will give us A minus lambda I and then times u equals to 0 vector. Now, already this u is non-zero vector. So if this product is to give us 0, then this implies this value here. And because it's a matrix now, for us to get what to multiply by another vector to get 0 vector, then we need to describe this one in terms of a scalar. And then if you have a matrix, what defines a scalar with respect to matrix is determinant. So therefore, determinant of A minus lambda times I should be the one that is 0, so that if you have 0 times a non-zero vector, you get a 0 vector. So this will be the equation that will be guiding us on how to find eigenvalues, eigenvectors. So i.e. determinant of A minus lambda I is 0. And the equation determinant of A minus lambda I equals to 0 is called the characteristic equation whose solution or solutions gives the characteristic roots or simply the eigenvalues. So that's what we have. And then before you get the equality, then the polynomial determinant of A minus lambda I is called the characteristic polynomial. For the matrix A. Now, so let's see how to solve. Now, note we are going to solve systems of first order linear differential equations of the form x dot equals to a x, where dot means first derivative with respect mostly to t. So these are the kind of equations that you are going to solve. So by definition, x dot means dx dt. So simply the dot here will mean differentiation, first derivative, and if you put two dots, then it means second derivative. So when you write x dot and then another dot, this means second derivative of x with respect to time. Sometimes the independent variable may be x, so that the capital X, the x the same as just x naught. So that's the convention. So if you put a dot here, then it means that you are differentiating with respect to time. If you put two dots, differentiating with respect to time twice. Okay, so the eigenvalue, the eigenvalue, eigenvector, method for solving linear first order systems of differential equations. So in this chapter, it is assumed that you already know how to solve solve differential equations without matrix method. So that the assumption is that you already have some knowledge on differential equations. Now, remember, if you have a second, just for example, if you have a second differential equation of the form, say, if you are given, so consider the equation, the differential equation d squared x dt squared minus 5 dx dt, and then plus 6x equals to 0. If you have this differential equation, then you know from basic discussion on differential equations to solve by method of characteristic. So we assume that x equals to e raised power rt is the solution. But we call this one 1 is the solution to equation 1. So which means dx dt. Now when you differentiate this one, you get r e raised power rt. This is just by chain rule. At the second derivative will give you, differentiating this one, you have r squared e raised power rt. So then now you substitute x dx dt dx squared x dt squared into the differential equation, and we have d squared x dt squared minus 5 dx dt equals to 6x will be r squared e raised power rt minus 5, where there's dx dt we put r e raised power rt, and then plus 6, where there's x we put e raised power rt equals to 0. And then e raised power rt is common, so e raised power rt, and then we have r squared minus 5r plus 6 equals to 0. And since exponential function can never be 0, then it implies that this coefficient r squared minus 5r plus 6 equals to 0. And so you solve this quadratic. Product is 6, sum is minus 5, numbers minus 2, minus 3. So that this will be r squared minus 2r minus 3r plus 6 equals to 0. And then you do pairing. So this be r into r minus 2 minus 3 into r minus 2 equals to 0. So r minus 3 and then r minus 2 equals to 0. And from this you get r1 is 3 and r2 is 2. So the solution, so therefore the solution, the general solution to equation 1 is x of t equals to c1 e raised power r1t plus c2 e raised power r2t, which will be x of t equals to c1 e raised power 3t, and then plus c2 e raised power 2t. So this becomes the general solution to that given differential equation. But our interest in this given section is not to solve, is not to use method of characteristics to find the solution of the differential equations. Ours will be to reduce the higher order differential equation into first order differential equations and then use method of eigenvalues, eigenvectors to solve the differential equation. This was just an appetizer for what you already know from your differential equations. Now, the same way we have taken to solve this question when you're doing method of characteristics, that you assume that the solution to the differential equation is x given by e raised power rt. So this is a starting point, this assumption. So for the case of eigenvalue eigenvector method, we still make the same assumption, but now we include the aspect of eigenvector. So since, or did this just say like, yes, I guess I'll say since for the case of real numbers, if we have this differential equation x dot equals to a t, then this means dx dt equals to this x dot equals to ax, this x equals to ax. So remember, a is a real number. Then this is the same thing as saying dx equals to ax dt, and then separate variables. So divide through by x, divide through by x, so that we have dx over x equals to a dt. And then now this is in separable form. Then you integrate both sides. So left hand side will give us ln of x. This will give us at plus c, where c is the constant of integration. Now, this means, this expression here means, remember ln, the base is e. So we have the same, this and this have the same meaning. So writing in exponential form, it means that e raised power at plus c is equals to x, and so x equals to e raised power at e raised power c, just loss of indices, or you can write this one as e raised power c, e raised power at, and so you can write this one as x equals to a e raised power at, where a is this constant e raised power c. So this means the solution to the differential equation x dot equals to ax is x equals to a e raised power at. So we are going to use this simple differential equation of first order to see how to get solutions to the general matrix equation x dot equals to ax dot. So similarly, if x dot is given by ax, where a is a square matrix, and x dot represents a set of first order differential equations, then to solve x dot equals to ax, we assume that the solution to the equation is x of t is given by e raised power now lambda t times u, where u is the eigenvector corresponding to the eigenvalue lambda. So now, let's see. So if we say that x is given by e raised power lambda t times u, then this implies that x dot, which is the same as dx dt, is the same as, so using, remember this is the one that has a t, so by chain rule we have lambda e raised power lambda t times u. And so this call this one 1. So replacing one in this differential equation, we get, so the x dot is lambda e raised power lambda t times u, which is equals to, actually remember we can put this to show that these are vectors, and then we have ax, so a, but x itself is e raised power lambda t times u. And so this can be written as lambda u e raised power lambda t is equals to a u e raised power lambda t, the same as a u is equals to a u e raised power lambda t is equals to lambda u e raised power lambda t. And you see, this is actually the same as saying au equals to lambda u, which is the eigenvector equation that we started with. So it tells us that now the assumption that x is given by e raised power lambda t times vector u will help us actually to solve the differential equation a x dot equals to a x, since if we simplify, we still get the usual eigenvector equation. And so solving that eigenvector equation, we'll be able to get the value of the eigenvector u and eigenvalue lambda. Because from this one, a u, and then take this to the left, minus lambda, now you need to put an identity matrix I, so that now the operation is defined because it's a matrix U equals to 0 vector. And then we have A minus lambda I times U, which is a 0 vector. So this implies that determinant of A minus lambda I, just as we have seen earlier, should be 0, so that this equation is satisfied. Remember, U is always a non-zero vector. So we will now illustrate how to solve systems of differential equations using eigenvector method. And then just lastly, so theorem. If U1 is a real eigenvector of A corresponding to the real eigenvalue lambda 1, then x1 of t given by e raised power lambda 1 t times u1 vector is a solution to the differential equation x dot equals to ax for all t. So this is another useful theorem, that if we have a real eigenvector corresponding to the matrix A for this eigenvalue lambda 1, then x1 of t given by e raised power lambda 1 t u1 is a solution to this given equation x dot equals to a x for all values of t. And then another theorem, what we call the superposition principle. So the superposition principle states that assume that x1, if you assume that x1 of t, x2 of t, up to x r of t are solutions to the differential equation. So assume that x1 of t, x2 of t, x3 of t, up to x r of t are solutions of this equation x dot equals to ax. Then if you get linear combinations of all these solutions, they will be solutions of the equation. So x of t is given by c1 x1 of t plus c2 x2 of t plus c3 x3 of t up to plus CR of X R of T with C1, C2, C3 up to CR arbitrary constants is a solution. So this is what we are trying to mean, that if X1 is a solution to this differential equation, X2 a solution to this differential equation, up to XR solution to this differential equation, then if you get the linear combination of all those solutions, is still a solution of the differential equation x dot equals to AX. And last theorem, that the vectors X1, X2 up to Xn are linearly independent if they satisfy the vector equation C1 X1 plus C2 X2 up to plus Cn Xn equals to 0 vector for all values C1 equals to C2 equals to Cn equals to 0. So that's what defines linearly independent vectors. And so with respect to this, suppose the n by n matrix A has different eigenvalues, lambda 1, lambda 2, up to lambda n, corresponding to eigenvectors U1, U2, U3, up to UN, then the eigenvectors U1, U2, U3, up to UN are linearly independent. So in the next session, we'll be doing now specific examples on how to use eigenvalue eigenvector method to solve differential equations. Thank you.